I'm Ramesh. In the last video, we have discussed the algebra of sequences. In algebra of a sequence, we find the relation between the position and term and express it with the help of algebra. And after that, I have given you an assignment. Do you remember? Have you done it? How was it? Anyway, let us check it. This was the problem. Write the sequence obtained by adding two adjacent consecutive terms in counting numbers starting from 1. Write the algebraic expression of this sequence. What is meant by counting numbers? The numbers which we use to count, that is 1, 2, 3, etc. Now, we have to find the sequence by adding consecutive terms or adjacent two terms. Which are the first two adjacent terms? 1 and 2. And what is the sum? 3. Now take the next two consecutive terms, that is 2 and 3. What is their sum? 5. Again take the next two consecutive terms, that is 3 and 4, and their sum is 7. Similarly, the sum of the next two consecutive terms is 9. Now the sequence is 3, 5, 7, 9, etc. This is a sequence which we have already seen in our last video, and we have seen that the algebra of this sequence is xn equal to 2n plus 1. Those who don't remember, I may just explain. 3 can be written as 2 plus 1, 5 can be written as 4 plus 1, 7 can be written as 6 plus 1, etc. So plus 1 is the last part in nth term also. What about the first part? For the first term, it is 2 or 2 into 1. For the second term, it is 4 or 2 into 2. In the third term, it is 6 or 2 into 3. And therefore, in the nth term, the first part is 2 into n or 2n. That is how we got the algebraic expression of this sequence as xn equal to 2n plus 1. We have already discussed that in every sequence there is a rule, and as the rule changes, there are different types of sequences. Today we are going to learn a particular type of sequences called arithmetic sequences. Have you heard of Halley's comet? It's a comet which passes the earth after every 76 years. Let me show you a picture of Halley's comet. This is Halley's comet. In 1682, the astronomer Edmund Halley observed an unusual phenomenon, a glowing white object with a long tail that moved across the night sky. It was a comet, a small icy rock that is flying through space while leaving behind a trail of dust and ice. Halley remembered that other astronomers had observed similar comets much earlier, one in 1530 and another in 1606. Notice that the gap between two consecutive observations is the same in both cases, 76 years. Halley concluded that all three observations were in fact of the same comet, which is now called Halley's comet. It is orbiting around the Sun and passes Earth approximately every 76 years. He also predicted when the comet would be visible next. Now let us look at a diagrammatic representation of this. In 1530, the comet passed Earth, and after 76 years, in 1606, it again passed the Earth. Again after 76 years, the comet again passed Earth in 1682. And again after 76 years, in 1758, the comet passed the Earth. Can you tell me when did the comet pass the Earth after that? After 76 years, right? And that is 1758 plus 76, that is 1834. Now, can you tell me when did the comet pass the Earth after 1834? Again, after 76 years, right? So, when was it? 1834 plus 76, that is 1910. Now, when did it pass after that? Again, after 76 years. Can you tell me when was it? It was in 1986. Now let me take all these numbers 1530, 1606, 1682, 1758, 1834, 1910, 1986. It is a sequence and each term is obtained by adding 76 to the previous term. Such a sequence is called an arithmetic sequence. Let me give you another example. Let us look at the multiples of 4, 4, 8, 12, 16, etc. Look at the first term 4. Add 4 to it, we will get the second term 8. Again add 4 to it, we will get the third term 12. If you add again 4 to it, we will get the fourth term 16. So it's also called an arithmetic sequence. Now look at the multiples of 5, that is 5, 10, 15, 20, etc. Look at the first term 5, add 5 to it, we'll get the second term 10. Again add 5 to it, we'll get the third term 15. So all these are arithmetic sequences. Now can you define what is an arithmetic sequence? First of all, it is a sequence. And are all the sequences arithmetic sequences? No. It's a particular type of sequence where the rule is addition. For every sequence, there is a rule. In the case of arithmetic sequence, the rule is addition. Addition by a particular number. Or in other words, we can say, in a sequence, if each term is obtained by adding a particular number to the previous term, it is called an arithmetic sequence. So, a sequence in which each term is obtained by adding a particular number to the previous term is called an arithmetic sequence. Here, in the case of Halley's comet, 76 is added to each term to get the next term. In the case of the multiples of 4, 4 is added to each term to get the next term. In the case of multiples of 5, 5 is added to each term to get the next term. And the number which we use to add is called the common difference. In the case of Halley's comet, the common difference is 76. In the case of multiples of 4, it is 4. And in the last case, it is 5. So, how can you define common difference? It is the difference between consecutive terms. 8 minus 4 is 4. 12 minus 8 is again 4. And if you take the next term, 16 minus 12 is again 4. So, we can define common difference as the difference between consecutive terms. That is, x2 minus x1 is common difference. x3 minus x2 is common difference. x4 minus x3 is common difference. Now, if you subtract 9th term from 10th term, it is again common difference. So, you can find common difference by subtracting a term from the term just preceding to it. Or we can say, in an arithmetic sequence, the constant difference obtained by subtracting any term from the preceding term is called its common difference. The difference is always same or common. Now let us take some more sequences and check whether they are arithmetic sequences or not. Let us take the sequence 1, 1.5, 2, 2.5, etc. It's a sequence which we have seen in our first video and we made it from a square. Is it an arithmetic sequence? Let us check. 1 plus half is 1 and half. 1 and half plus half is 2. 2 plus half is 2 and half. So it's an arithmetic sequence with common difference half. Now let us take the sequence of sum of outer angles. Sum of the outer angles of a triangle is 360. Sum of the outer angles of a square is 360. Sum of the outer angle of a pentagon is 360. So the sequence is 360, 360, 360, etc. Is it an arithmetic sequence? Nothing is added, right? So we can consider 0 is added. 360 plus 0 is 360. And if you add again 0, you get the third 360. That means it is also an arithmetic sequence with common difference 0. Now let us take another example. 10, 8, 6, etc. Is it an arithmetic sequence? How the terms are obtained? 10 minus 2 is 8. 8 minus 2 is 6. So here nothing is added but it is subtracted, right? But we can consider subtraction as addition. But we know subtracting 2 is equal to adding negative 2. So instead of saying subtracting 2 from 10 to get 8, we can say add negative 2 to 10 to get 8. So here also a number is added, but that number is negative. So we can say it's also an arithmetic sequence with common difference negative 2. So we have seen that the common difference can be positive, it can be negative, it can be 0. And we can observe one more thing. Look at the first example. The common difference is a positive number. Half, it is a positive number. Now look at the terms 1, 1 and a half, 2, 2 and a half, etc. The terms goes on increasing. So when the common difference is positive, the terms goes on increasing. And in our second example, the common difference is 0 and you can see that the terms are not changed. It remains unchanged. So when the common difference is 0, the terms remains unchanged. And in the last example, the common difference is negative. And we can see that the terms goes on decreasing 10, 8, 6 and after that it will be 4. So the terms goes on decreasing because the common difference is negative. So when the common difference is positive, the terms goes on increasing. When it is 0, it remains unchanged. And when it is negative, it goes on decreasing. And again, the common difference can be fractions, decimals, rational numbers, irrational numbers. It can be any type of numbers. Now let us take some more examples. Let us take sequence of multiples of 3. The first multiple of 3 is 3. Second multiple is 6. Third multiple is 9. So the sequence is 3, 6, 9, etc. Is it an arithmetic sequence? Let us check. 3 plus 3 is 6. 6 plus 3 is 9. So it's an arithmetic sequence with common difference 3. Now let me take another sequence using 3. The sequence of numbers which leave remainder 1 on division by 3. We have seen this sequence. It was 1, 4, 7, etc. Is it an arithmetic sequence? Let us check. 1 plus 3 is 4. 4 plus 3 is 7. So it's again arithmetic sequence with common difference 3. Now let me take one more sequence using 3. The sequence of natural numbers which leave a remainder 2 on division by 3. We have seen this sequence also and the sequence was 2, 5, 8, etc. Is it an arithmetic sequence? 2 plus 3 is 5, 5 plus 3 is 8. So it's also an arithmetic sequence with common difference 3. So here I have made 3 sequences using 3. When you take all the natural numbers, they can be divided into 3 sequences. The multiples of 3 are the numbers which leave a remainder 0 on division by 3. Secondly, the numbers which leave a remainder 1 on division by 3. And thirdly, the numbers which leave a remainder 2 on division by 3. Here we have seen that all these are arithmetic sequences and also we have seen that their common difference is same, and that is 3. Now let me give you an assignment. You take the number 4. How many sequences can be made from natural numbers in this way using 4 sequences, right? The multiples of 4, or the numbers which leave a remainder 0 on division by 4, and then the numbers which leave a remainder 1 on division by 4, then those with leave a remainder 2 on division by 4, and the numbers which leave a remainder 3 on division by 4. So write all these 4 sequences and find out the common difference and check whether they are same or different. And after that, you can go to the number 5 and make the sequences, the multiples of 5, numbers which leave a remainder 1 on division by 5, then 2 on division by 5, then 3 on division by 5, and then 4 on division by 5. And again, check whether they are arithmetic sequences or not and find out their common difference. And doing so, check whether you can make some generalizations or not. Tell me about your findings. You can comment it or you can inform me in other ways. Let me see how you do it. Now I am going to make another sequence with 3 itself, the powers of 3. What are the powers of 3? 3 raised to 1, that is 3. 3 square, that is 9. 3 cube, that is 27. Is it an arithmetic sequence? Let us check. 3 plus 6 is 9. 9 plus 6 is 15, not 27. That means the difference is not common. There is no common difference. So it's not an arithmetic sequence. Now let us do some problems. Check whether each of the sequences given below is an arithmetic sequence. Give reasons. For the arithmetic sequences, write the common difference also. Sequence of odd numbers, sequence of even numbers, sequence of fractions got as half the odd numbers, sequence of powers of 2, sequence of reciprocals of natural numbers. First of all, let us take sequence of odd numbers. We know the sequence of odd numbers is 1, 3, 5, 7, etc. Is it an arithmetic sequence? Let us check. 1 plus 2 is 3. 3 plus 2 is 5. 5 plus 2 is 7. So it's an arithmetic sequence with common difference 2. Now the second problem, sequence of even numbers. What is the sequence of even numbers? 2, 4, 6, 8, etc. Again, 2 plus 2 is 4. 4 plus 2 is 6. So it's an arithmetic sequence with common difference 2. Now the third one, sequence of fractions got as half the odd numbers. Odd numbers are 1, 3, 5, etc. Half the odd numbers means 1 by 2, 3 by 2, 5 by 2, etc. Now is it an arithmetic sequence? Let us find the difference between second term and first term and third term and second term and check whether they are equal or not. x2 minus x1 is 3 by 2 minus 1 by 2. Now the denominators are same. So 3 minus 1 all divided by 2. And 3 minus 1 is 2. So we get 2 by 2 and that is equal to 1. Now what is 5 by 2 minus 3 by 2? 5 minus 3 by 2 or 2 by 2. Again 1. So the difference is same. So it's an arithmetic sequence with common difference 1. Now the fourth problem, sequence of powers of 2. That is 2 raised to 1, 2 raised to 2, 2 raised to 3, etc. That is 2, 4, 8, etc. Is it an arithmetic sequence? Let us check. 2 plus 2 is 4. 4 plus 2 is not 8 but 6. That means it is not an arithmetic sequence as there is no common difference. Now the last part, sequence of reciprocals of natural numbers. What are the natural numbers? 1, 2, 3, etc. What is the reciprocal of 1? 1 by 1 or 1 itself. What is the reciprocal of 2? 1 by 2. What is the reciprocal of 3? 1 by 3. So the sequence of reciprocals of natural numbers is 1, 1 by 2, 1 by 3, etc. Is it an arithmetic sequence? Let us check. When you subtract half from 1, we get 1 by 2. Again, if you subtract half means we will get 0. But 0 is not there. It is 1 by 3. That means minus half is not the common difference of the sequence. So it is not an arithmetic sequence. Second problem. Look at these pictures. If this pattern continue, do the numbers of colored squares form an arithmetic sequence? Give reasons. In the first figure, there are 8 colored squares. In the second figure, there are 12 colored squares. And in the third figure, there are 16 colored squares. So the number of colored squares is 8, 12, 16, etc. Now let us check whether it is an arithmetic sequence or not. 8 plus 4 is 12. 12 plus 4 is 16. So there is a common difference 4. So this is an arithmetic sequence. Now you can count the colored squares easily. I'll give you an easy way to count. Let me take the first square and take two squares together to form a rectangle. So there are 4 equal rectangles and each one contains 2 squares. So altogether there are 4 into 2, 8 squares. Now look at the second figure. We can take 3 squares together to form a rectangle. So there are again 4 rectangles and each one contains 3 squares. So the total number of squares is 4 into 3 or 12. Now let us take the third figure. Let us take 4 squares and form a rectangle. So there are 4 rectangles, equal rectangles in which there are 4 colored squares. So the total number of colored squares is 4 into 4 or 16. In this way you can count the number of squares easily. Now the third problem. See the picture below. How many small squares are there in each rectangle? How many large squares? How many squares in all? Continuing this pattern, is each such sequence of numbers an arithmetic sequence? First of all, let us check what is meant by a small square and what is meant by a large square. Look at the first figure. You can see two small squares in that picture. So each one is a small square. So this is a small square, and using this so many times, all other figures are made. Now what is meant by a large square? Can you make a square using two such small squares? It's not possible. We need at least 4 such squares to make another square like this. And this is the largest square in this case. And in our problem, we cannot make squares larger than this. Now the first part of the problem, we have to count how many small squares are there in each figure. Let us check. In the first figure, how many small squares are there? There are only 2 small squares. Now let us look at the second figure. How many small squares are there? 4, right? Now let us look at the third figure. How many small squares are there? Very good, 6. Now let us look at the fourth figure. How many small squares are there? 8. Very good. Now let us write it as a sequence. The sequence of small squares is 2, 4, 6, 8, etc. Now let us look at the second part of the problem. We have to find how many large squares are there in each figure. Let us look at the first figure. Is there a large square? No, there are only two small squares. So there is no large squares. So the number of large squares is 0. Now look at the second figure. There are 4 small squares and combining them we get a large square. So how many large squares are there in the second figure? One and only one. Now let us look at the third figure. We have already seen that there are 6 small squares. Now we have to find how many large squares are there in this figure. This is a large square and you can draw another large square like this. So altogether how many large squares are there in this third figure? 2. Right? Now let us look at the fourth figure. We have already seen that there are 8 small squares. Now we have to find how many large squares are there in this figure. First of all, we can take the first 4 small squares and we can make a large square like this. Now take the 4 small squares at the middle and you can make another large square like this. Now take 4 small squares at the end and you can draw one more large square like this. So altogether, how many large squares are there in the fourth figure? 3. Very good. Now let us find the sequence of large squares. In the first square there is no large square, so the number is 0. In the second figure it is 1. In the third figure it is 2. And in the fourth figure it is 3. So the sequence of large squares is 0, 1, 2, 3, etc. Now we have to find the sequence of squares in all, or we have to find the total number of squares in each figure. We have already got that the sequence of small squares is 2, 4, 6, 8, etc. That is, there are 2 small squares in the first figure and there is no large square in the first figure. So altogether there are only 2 squares in the first figure. And in the second figure there are 4 small squares and 1 large square. So altogether there are 5 squares. Now in the third figure there are 6 small squares and 2 large squares. So altogether there are 8 squares. Now in the fourth figure there are 8 small squares and 3 large squares. So altogether there are 11 squares in the fourth figure. So the sequence of all the squares is 2, 5, 8, 11, etc. Now let us check whether all these sequences are arithmetic sequences or not. The first sequence, the sequence of small squares is 2, 4, 6, 8, etc. We know it's an arithmetic sequence with common difference 2. And the second sequence, the sequence of large squares 0, 1, 2, 3, etc. It is also a sequence with common difference 1. Now what about the sequence of all squares 2, 5, 8, 11, etc. It's also an arithmetic sequence with common difference 3. So all these 3 sequences are arithmetic sequences. Now the fourth problem. In this picture, the perpendiculars to the bottom line are equally spaced. Prove that, continuing like this, the length of perpendiculars form an arithmetic sequence. Let me take the figure and draw lines like this. Then we get some triangles which are shaded here. Now look at each triangle. These sides are equal. Why? Given that the perpendicular lines are equally spaced. So these lines are equal. Now look at this angle. How much is it? It is 90 degree. This is also 90. This is also 90. This is also 90. Now all these are parallel lines and this line cut those parallel lines. So all these angles are equal as they are corresponding angles. So what did we see? In each of these triangles, one side and angles at the end are equal. Means all these triangles are equal triangles. And we know for equal triangles, all the sides are equal. So this length is equal to this length, and that is equal to this length, and that is equal to this length. Means the perpendicular increase in each case is same. That means to this line, this much is added to get the second line, and the same length is added to the second line to get the third line, and the same length is added to the third line to get the fourth line. So the same length is added to each line to get the next line. So it is an arithmetic sequence. Now the fifth problem. The algebraic expression of a sequence is xn equal to n cube minus 6n square plus 13n minus 7. Is it an arithmetic sequence? The algebraic expression is given as n cube minus 6n square plus 13n minus 7. Let us find the first term. How can we find the first term? Put n equal to 1. So x1 equal to 1 cube minus 6 into 1 square plus 13 into 1 minus 7. 1 cube is 1 and minus 6 into 1 square equal to minus 6. 13 into 1 is 13 and minus 7. Now let us add the positive numbers. 1 plus 13 is 14 and minus 6 minus 7 is minus 13. So we will get 14 minus 13 and that's equal to 1. That means the first term of the sequence is 1. Now let us find the second term. Put n equal to 2. We will get x2 equal to 2 cube minus 6 into 2 square plus 13 into 2 minus 7. 2 cube is 8. Minus 6 into 2 square is 24. 13 into 2 is 26 and minus 7. Again let us add the positive numbers. 8 plus 26 is 34. Minus 24 minus 7 is minus 31. Now 34 minus 31 is 3. The second term of the sequence is 3. Now the third term is x3 equal to 3 cube minus 6 into 3 square plus 13 into 3 minus 7. 3 cube is 27. 3 square is 9. Minus 6 into 9 is minus 54. 13 into 3 is 39 and minus 7. Again let us add the positive numbers. 27 plus 39 is 66. Minus 54 minus 7 is minus 61. Subtracting we will get 5. The third term is 5. First term is 1, second term is 3, third term is 5. Is it an arithmetic sequence? Let us check the fourth term also. What is the fourth term? 4 cube minus 6 into 4 square plus 13 into 4 minus 7. 4 cube is 64. 4 square is 16. 16 into minus 6 is minus 96. 13 into 4 is 52 and minus 7. Let us add the positive numbers together. 64 plus 52 is 160. Minus 96 minus 7 is 103. Subtracting, we will get 13. Now look at the terms 1, 3, 5 and 13. Is it an arithmetic sequence? 1 plus 2 is 3, 3 plus 2 is 5, 5 plus 2 must be 7. But here the fourth term is 13. So it is very clear that it is not an arithmetic sequence. But if you have looked at the first three terms, you may think that it's an arithmetic sequence. But looking at the fourth term, we can easily understand that there is no common difference. So this is not an arithmetic sequence. So today we have learned arithmetic sequences. A sequence in which each term is obtained by adding a particular number to the previous term is called an arithmetic sequence. And we have discussed common difference. It is the difference between consecutive terms of an arithmetic sequence. In an arithmetic sequence, the constant difference obtained by subtracting any term from the preceding term is called its common difference. And the common difference is denoted by the letter D. So we can say D equal to x2 minus x1 or D equal to x3 minus x2 or D equal to x6 minus x5 or D equal to x98 minus x97, etc. And we have seen that the common difference can be positive, negative or 0. When the common difference is positive, the terms goes on increasing. When it is negative, it goes on decreasing. And when it is 0, the terms remains unchanged. And also we have seen that the common difference can be any number, can be fractions, decimals, natural numbers, rational numbers, irrational numbers. It can be any type of numbers. Now let me give you an assignment. Write down all the sequences which we have discussed so far in the first video and in the second video, or you can refer to the textbook up to which find out all the sequences which we have discussed. Which of them are arithmetic sequences? Find their common difference. Try to do it. When you do it alone, you will learn easily and you can remember it forever. So do it well. Hope you have all understood. I'll be back with another video. Till then, bye.